So if not, then let me review what we did last time. So here is the brief summary of what we did. Okay. So essentially, we are looking at rapid flows. This is where momentum transfer happens because of interparticle collisions, and we were looking first at a case. We solved shear flow in zero gravity. But then we said, okay, supposing the system is isothermal, that is, the granular temperature is constant throughout. In that case, we found that the pressure is just a constant. And so that means that the spacing S is also constant. We found the pressure, shear stress is given by this. Here both temperature and the spacing are constant. So you get this proportional to this. And we can easily integrate this equation to give us the velocity profile, which just turns out to be linear. So this is what you will get for a Newtonian fluid also, a linear velocity profile when you shear it between parallel plates. And then if you look at the energy balance equation, because there is no conduction term since the temperature is constant, so dt by dy is 0, you get this, and you get an expression for the temperature. And what it says is the granular temperature is proportional to the velocity gradient squared. And what I said is that this result is quite general, because whenever you have no conduction, then you'll get reduced to this equation. And so you'll get this regardless of what the flow is. So this is one thing that we did. Then we looked at a historical theory, the first one that was presented by Bagnold, 1954. And through just some arguments, simple arguments like how much momentum will change per collision, that is mass times delta U, and then number of collisions per unit time, that's proportional to shear rate, and then you get forces given by rate of change of momentum, that is change in momentum per collision into number of collisions per unit time, and then stress is force per area, where area is just 1 by the area is just diameter squared. And so if you simplify everything, you get one key and very important result is that the shear stress is proportional to the velocity gradient squared. And this is really known as the Bagnold stress. But what we also saw is that the half theory also predicts exactly what the Bagnold theory predicts. Because if we take this temperature to be proportional to the velocity gradient squared, and then you put that into this equation for the shear stress, then the equation for the shear stress becomes like this, which is exactly what Bagnold got. So basically, half theory reduces to the Bagnold theory when you have shear flows with no conduction. And then we looked at a simple example of flow down an inclined plane. And for this, we assume that the velocity is in the x direction and varies only in the y direction. And for that, the x momentum balance becomes this, the y momentum balance becomes this, and the energy balance gives us this. And if we solve for everything, you can integrate and get the pressure profile, the stress profile, and you can get the shear stress. And then if you invert this, because we know this is shear stress is given by this expression, so we can, when we invert it, you'll just get the velocity gradient is just square root of the distance here, y, square root of y into a constant. And then if you integrate it, you will get this, which is called the Bagnall profile, where A is just given by this quantity. So this has been essentially validated by experiments and so forth. So the Bagnall profile, or even the half profile, whatever you want to call it. And today I want to show you some simulation results, and then we'll talk about a sort of dense flow. So we've looked at very slow flows where friction dominates. Now we've talked about rapid flows where collisions dominate. Now we can think of, something in between where both are sort of equally important, and those flows are called dense flows. And I'm going to show you one model for those kinds of dense flows, and then we'll do some examples. So let me just show you first the simulation results. Of course, there are lots of experiments which also prove that Bagnall theory and all this works, but I wanted to show you one set of simulation results which were done quite long back, and this is done in 2001. And they did granular flow down an inclined plane, Bagnall scaling and rheology. So this is a group at, actually the main people are the Sandia National Laboratory. And this is the main fellow, Plimpton. So today, they essentially started this, and they are the creators of lamps. So what we are teaching and we are using so freely, and it's so easy to use, we have to thank them for doing that. Anyway, so this is an early paper, and they looked at this very simple system. You have an inclined plane, which is quite rough, and this plane is inclined at an angle theta. And there are periodic boundary conditions in the y direction and in the flow direction. So x is the flow direction, y is the direction normal to the flow, and z is the height. And one of the things that they found out is that as you increase the angle, first, if your angle is too low, there will be no flow. Then as you go on increasing the angle, then you get stable, steady flow. And then if you go beyond a certain angle, what happens is that, the flow never reaches steady state. The velocity goes on increasing. And the reason for that is that the dissipation is not quite enough to balance the stress, viscous stress is not enough to balance the gravitational force that is driving this. So this is exactly the same problem that we solved also, flow down an inclined plane, for which we got the Bagnall profile. And these people have done the analysis using lamps, now what we call lamps, but at that time it was their own program. And so if we look at the region where the flow is steady and so forth, this is what you will get. So this is the height Z. Phi is the solid volume fraction, and you can see that it's almost constant except near the base and near the free surface. And if this is the velocity as a function of height, at the base the velocity is 0, so you have a no slip boundary condition here, because this is because the base is quite rough. and then it increases, and you get different values of theta, I mean different profiles for different angles of inclination. So as you go on increasing the angle of inclination, the velocity increases. And there are two different models that are used for the interparticle forces. The symbols are for the Hooke model and the lines are for the Hertz model. So they give slightly different results. Of course, depends on the parameter values also. And they could also calculate the granular temperature as a function of height, and you can see that it varies. This is not quite an isothermal system. And 0 is the base, so the temperature is highest near the base, and then it goes to a low value near the free surface. But the thing to realize is that though they haven't given the actual magnitude of the granular temperature, if you look at the velocity, okay, even these, they have not given the actual magnitude. But if you just look at the magnitude of the granular temperature to the mean velocity, it is lower by a factor of 10. So the fluctuation velocities are quite small. And here they show also what is the effect of coefficient of restitution, and you see it has almost no effect on the profiles. And then this is on the stiffness of the particles going from 4 to 6. And again, there's very little effect of stiffness. And finally, this is the comparison to Bagnold model. And so these very light lines are for the Bagnold model. And what they're comparing is actually the shear stress versus, the shear stress versus the shear rate. So you should get a square, and you're getting very close. The match is extremely good, except of course near the base and near the free surface. But otherwise, there is a very good match with the Bagnold theory. Okay. So now let me go on and tell you a little bit about the next thing, which is a new model for so this is what we were doing last time, and we came to Bagnold profile. Now I've shown you that how the Bagnold profile works so well. I mean, it gives such a good agreement with the computational results. And I can show you even more. Some students who have worked in our lab have shown a really excellent results, and I'll put some of those results also up. So what is the date today? Today is the 30th of September, and this is lecture number 26. Just put some gap. Okay. So what we have already seen here is we showed some simulation results, which are validation of Bagnold and theory. And this is, of course, in the presentation. So just to keep it as a record that we did go through that. And today what I want to talk about is, just the third sort of type of model where we want to look at dense flows. So what we looked at is slow flows, where your inertial number is much less than 0.1, and we looked also at rapid flows in which the inertial number is much greater than 0.1. And in between these two limits, we have what we call dense flows. And here mainly we had friction. In this we had mainly collisions. And here we can think of this as both. Okay. And so this is what we want to really look at. How do you deal with this? Now there are many ways of looking at it, but I want to tell you about one model which has turned out to be quite successful in recent times, and that model is based on the inertial number, and actually there was a lot of work that went on first, and what many studies showed that if we, and this is based on many sort of empirical studies. So there is this model in which they basically postulated that mu, which is something like shear stress divided by the pressure, should be a function only of the inertial number. This is just based on what results they had. And the volume fraction also should be a function only of the inertial number. So this is what was the postulates of the model. That means that you have a ratio between the shear stress and the pressure, which depends only on the inertial number. And just to remind you, the inertial number, which we defined early in the course, and we have mentioned many times in between, this I is just equal to gamma dot, the shear rate, into the particle diameter divided by the pressure by particle density raised to the power of half. So this is what is the inertial number here. And so what they said is this is a dimensionless number. Mu is also dimensionless. It's the ratio of two stresses. So it's a dimensionless number. So they said this dimensionless number can only depend on this dimensionless number. And then the volume fraction can also depend only on this. And what they found from many experiments and so forth is that this in fact holds true for many cases. And what they find is that mu, if you plot as a function of I, it essentially goes like this. And if you fit a line to the data, then what you get is mu is equal to mu 0. I'm sorry, just to use the same notation, mu is equal to mu s so there are actually three constants. So you can see when I goes to infinity, so if I goes to infinity, then you know, this term goes to 0, and so then you just get mu s plus mu2 minus mu s. So you essentially get mu is equal to mu2 as I goes to infinity. And if you put I equal to 0, then this term becomes infinite. So this whole term drops out, and you see that mu is equal to mu s for I equal to 0. So those are the two limiting cases. So, if I have to draw this, then here this is mu s, and I'm sorry, this is mu2, and this one is mu s. So this is what the curve looks like. And this is an empirical expression. So it's not based on any theory, or it's not based on some principles, but just based on whatever data they were able to collect, they could get this. And you can see that the I0 is the third parameter. And when I is equal to I0, you'll see that mu, so for I equal to I0, what you get is mu is equal to mu s plus mu2 minus mu s divided by 2. So, if you simplify this, you'll see that mu is just equal to mu2 plus mu s by 2. So when I is equal to I0, you will get, if you take the midpoint of these two things, that is mu s by mu2, mu s plus mu2 divided by 2. So this line is that. Then wherever it meets here, then this point is I0. So this is what the expression looks like. And through experiments, they also found that if you make a similar plot of phi versus I, then you get a really simple behavior, that is that you have a linear variation where you can write this in a mathematical form as just phi is equal to phi max plus phi max minus, I'm sorry, times I. Something like this. Or, you don't, don't even bother about that. You can just say C times I, where C is just a constant. So this slope is just equal to C. And you can put it as phi max minus phi min also, but of course we don't know what is phi min then. Okay. So this is the model. This is the simple model. So here we have mu, which is shear stress by pressure, and phi. So how do we use this model? Well, supposing we want to try and use it. Well, one thing that we can do is we can try and define, the viscosity. Okay. So how do you relate mu to viscosity? So you can clearly see that if you are given mu, then you can easily calculate so we have defined mu as equal to tau xy by p. So this gives us that tau xy is equal to just mu times p. And this gives us, now eta is just defined as tau xy by the shear rate. The shear stress by shear rate is called the apparent viscosity. And now if you substitute for this, this is just equal to mu p by gamma naught. So now here you have the simple thing that if you are given mu, then you can easily calculate the viscosity. So the viscosity is just mu p divided by gamma dot, where gamma dot is a shear rate. Okay. So this is the relationship. And now we can extend this model to full 3D flows. So we know the viscosity. So then what we can write is that we can write a tensor equation for the stress. We have seen this in fluid mechanics a lot. For a Newtonian fluid, this eta is equal to mu, which is the viscosity. Here we are calling eta as the viscosity. So this is what you will get. But this is a sort of frictional model also. So we say that this is true only if the shear stress, the magnitude of the shear stress is larger than a yield stress, and D is equal to 0 if tau is less than or equal to the yield stress. So this is what you would write. So this is essentially the equations for a Bingham fluid. I hope. Have you all come across this Bingham fluid?
Yes, sir.
Yes, no? So this is just a Bingham fluid. But now we want to include the mu I model, that is what we have just defined, into this Bingham fluid, because we know in a solid that sometimes you will get regions where there is no flow, that is when D is equal to 0. Remember D, we have defined it many times before, this is the rate of deformation tensor. So wherever D is 0, that means that there is no flow. There's no deformation, so no flow. Of course, over here, tau is the magnitude of the shear stress, and it's defined as just the tensor tau double dotted with itself and then divided by 2 raised to the power of half. So this is the definition of tau. And I'm going to write down what is tau y. And for this model, your tau y is just given by mu s into p. So, you can see from here that, your mu cannot go lower than mu s. The minimum value of mu, even at I equal to 0, the minimum value is mu s. So that means you have to have your stress has to be, if there's flow, then your stress has to be greater than mu s times p. So this is where this tau y comes from. So this is interesting because the yield stress is not a constant, but because this is a granular material, you actually have a yield stress that depends on the pressure. So higher the pressure, higher the yield stress. So this is the definition of the model. And the last thing to write down is eta, as we have seen before, is just mu p by gamma dot. And gamma dot also can be written in tensor form, and that we have seen also before is just 2 times d double dot d raised to the power of r. So this completes the specification of the constitutive model. So this whole thing is the constitutive model or the constitutive equations. And these determine the material or the flow properties or the rheology. And then, of course, you have the balance equations. And those are the continuity, which is just divergence of u is equal to 0. And we have the momentum balance equation, which is rho b del u by del t plus u dot gradient of u is equal to minus gradient of p plus divergence of tau plus rho g. So what is missing? We don't need an energy balance equation. It's not required since the constitutive model does not. Oh, I don't know why my pencil is not working. Does not contain the granular temperature. So if you see this constitutive model, what is interesting is that in kinetic theory, the viscosity depends on the temperature. But what we have done is we have replaced temperature by pressure. So here the viscosity is related to the pressure rather than the temperature. And hence we eliminate the temperature, and so it becomes much simpler. You can just solve this equation. Okay, so I'm going to end this right here. And now what we'll do is we can log out of this like we have been doing in every quiz. We can log out of here and then log into group 1 or group 2. So I'll start the meetings for group 1 and group 2. So you go in there and put on your camera so that we can see you taking the quiz. The quiz is on Moodle as before, and so you will have 15 minutes to do the quiz. So I will see you now in group 1, and I think